Hello. So, thank you all for coming. I know it's been a very long and exciting droidcon. I am Ash Davis. I'm a senior engineer at Snap Mobile in Berlin, Germany. And I'm going to be talking today about demystifying molecule. It's not just another Compose talk, I promise. This is actually about using Compose in environments where, well, we wouldn't really normally do so. So taking a tool that was meant for this and using it for something we shouldn't do. But it's fun. So when I first gave this talk, it was in collaboration with Bill Phillips, who is a contributor on the project. It was in New York. You can check out the video for that as well. Hopefully this does it justice. Let's get started. So yeah, this whole sort of thing started with a tweet, as things do, about me playing around with using Compose in a non-UI sort of headless environment. It was actually for a cloud function, because why not? And I kind of stumbled into the molecule library, and I wanted to try it out. And I was like, well, so why there's no documentation about how to, build your own compiler, how the guys from Molecule actually did this in the first place? So, of course, this resulted in Bill challenging me and saying, do a talk about it. And I was like, well, I can't back down from a challenge like that. So this is the result of said challenge. So it's likely everyone here has already heard of Compose UI, and if they haven't, they have at least heard of it after today. So Jetpack Compose is the new shiniest thing for Android, and we should all probably be using it at least in some capacity in our projects. A quick sort of covering overview to just cover the features. So it's inspired by sort of reactive tools to allow you can define your user interface in a kind of functional way without kind of manually modifying the view state. And it does that idea with composition. So you've got this screen here where you've got a few UI elements, and you can end up with kind of basic login form that's going to look a little bit like this. Really kind of straightforward, just text in declarative functions so you can see what's going on. So if you were to sort of execute this function, the real nice thing about Compose is its idea of recomposition and how it can actually take different inputs and be very clever about what it needs to recompose and what it needs to reproduce. And it has all these efficiency optimizations built in. So calling this UI function with this input, would actually, for the first time, its initial load would actually execute everything. But if, for example, you change one of the elements in the argument to Ash Davies, for example, it would know to only recompose the parts that are actually relevant for that input. So it would actually only recompose the text here. So you're gaining from all this efficiency optimization. Now, for the same reason, Compose will, recompose and execute your function any number of times in your lifecycle for any number of reasons, really. So Compose allows you to introduce this idea of a snapshot state, which retains and preserves your state through executions and invocations of a function. So you can use remember functions with mutable state to kind of keep this in your snapshot state, and then if you then refactor on submit to take a few different things with the method signature here, you can actually then pass that into the view. There are lots of different ways of doing this, and I won't bore you with all the different ways of using remember or property delegates or all these different things, because these are more pertinent to Compose. And let's get into the nice parts of actual using, not UI. So say we want to start thinking about building a kind of domain behavior. Now, we're still locked into the UI part here, but so, for example, we want to use a session service and have a progress indicator going on here. We'd have to kind of modify this a little bit, but having everything inside this function showing this progress indicator if we're doing something with this session service. And the username is being handled by the mutable state here, and everything is handled in the same lifecycle as it should be. But the problem with this, as you might be able to see, actually, is its testability. Now, it's really difficult to kind of test this behavior because, well, in order to actually get a result from this, you have to execute everything. So you can't actually validate anything without executing everything. So, you've got all sorts of individual behaviors that you can't actually test properly. So often the most common way of doing this or separating this or creating a seam or whatever you want to call it is to sort of create this concept of a UI model and a UI event. This is more common, and you see it in a lot of modern applications. And it defines like an object protocol. in which these two elements will actually operate. And if you're saying this, well, this is just unidirectional data flow, then thumbs up, it is. It's not a new concept, but it is an important one. So now we're factoring this to kind of taking our UI models and our UI events, we can actually then use this stripped down of the same thing, which is much, much easier to read and much easier to test. And now we're only concerned with the state, and we're free to move the business logic somewhere else. So it might look like a presenter. You might have a session service, and it's got some sort of very naive navigation paradigm here. And using only the APIs we kind of define in the presenter, we would also have the business logic. So this is where I'd like to jump into the motivation of doing so, like stepping back a bit to think about how we build our business logic and domain behavior. And back in the day, this is a wonderful slide that Bill kind of took me by surprise with, and you can see some lots of very modern Android approaches here. So yeah, this is just an example of bad architecture. Maybe I should have lent this to the presentation from this morning. But it's a demonstration of how we might have done this in a very naive early times. Handling this presentation logic and having like an asynchronous task, having some background behavior. And of course, don't do this, but this was sort of a precursor to a lot of decisions that introduced reactive architecture into our applications. So, reactive programming in RxJava was sort of a revolutionary term for this. And that was our original solution to having async tasks. And years ago, RxJava was the go-to de facto solution. Reactive pipelines defined a sequence of operations that could be applied to a state, and this was replayable. It was giving us a chance to actually explicitly handle threads, whereas normally you might have a very difficult situation where you're having to create and manage the thread yourself, whereas RxJava sort of gave us this visibility about having background thread operations and which and where to do our UI operations on the main thread. So it sort of brought that to the foreground of our attention. Foreground, pun intended. And it sort of introduced the concept of inline error handling. You might remember this like do on error lambda that you could call on Rx pipeline. So these sort of nice Rx behaviors sort of introduced this behavior and concepts to us in general. And the concept of lifecycle awareness. You might have been able to create a composite disposable or the kind of execute the handle that would represent this sequence of operations that you would then cancel in non-destroy, for example. So I'd like to kind of call back to this presentation from Jake Wharton from actually 2017, where he's talking about reactive pipelines and the difficulties of merging all these different things together from different data sources, where you might have like a local data source and a remote data source and a caching and all these different things where you might want to actually merge these in together. And it's very pertinent to this problem because we keep on coming back to it, addressing it with maybe a different approach, maybe a different technology. And that's kind of what we're doing here today. So a very naive approach to this, putting aside all architectural decisions, MVP, MVVP, MVI, DVI, RSVP, aside, this is what like a naive Rx login presenter might look like. And it's peppered with all these little kind of Rx operators that you sort of have to be au fait with to understand and kind of get clear with. But more explicitly, it doesn't have a very logical sequence of operations. You're not kind of able to look at it and read it from top to bottom and think, I know what's going on here. For a start, look at where start with is. It's like start with right at the bottom, and that's not really a logical place to think that's the start, unless you're watching a Quentin Tarantino film. So yeah, it's really sort of difficult to see the sequence of operations here. Let's not forget all this ridiculous operations of single to flow mapping and to single to observable to maybe, and then having all these nullable things, and then Rx Kotlin, and well, that was a headache. Also, I'd like to highlight, I'm not personally responsible for this code, but it was an example of production code that I found. So the names have been changed to protect the identity of the author, but this was an actual live snippet of an Rx sequence chain that is just completely unreadable. So yeah, that escalated quickly. So enter the new savior. We've got Kotlin coroutines. The imperative strikes back. And there was a discussion we had, I think at Berlin DroidCon a couple of years ago, which was entitled RX Java Must Die. And this is a really fun discussion because we were discussing about how coroutines as a first-class language concept would be able to kind of replace all these functional types. And it was really cool. And it was a native library. You'd have less of this kind of Yoda syntax code where you've got start with at the bottom and then, this really weird things. And more importantly, that it introduced the concept of having a suspended function as a method signature. So actually as an operator part of the language support. And I thought this was really, really cool because it's important to identify here this is Kotlin.coroutines, not KotlinX.coroutines. So this is actually part of the first class language support. Granted, you couldn't really build a coroutine without Kotlin X, but the point was here is that you're moving away from this reactive to a quasi-imperative style structure. But then we also started seeing things moving from observable to flow, and we're getting the same issues just with a different name. But let's take another approach at writing our presenter with coroutines here. Basically the same thing, but written with a flow abstraction instead. It improves the order of declaration, and it does kind of give us a better cognitive load with this, but it doesn't really kind of solve all the problems that we had from RxJava. We're still using flow as analogous to kind of observable, and it still has this kind of complex operations that's not so fantastic to follow when you're trying to understand the complex data flow. And adding to this, as if you've ever worked with like a real-world example, it's hard to show this as a contrived solution, but if you're familiar with real-world business applications, they tend to grow organically over time, adding more requirements, adding more services, adding some other decision from a product owner who thought it'd be great to include a calculator in there because reasons. But you're getting all these different kind of requirements. So you ended up with these very weird sort of RX-style combine operators, or map with latest, flat map with latest, combine with this, combine first, combine last. And it's just a little bit overloading because you're having to then change the same code over and over and over again. And if you're familiar with the beloved solid principles, this obviously violates open closed. Not that I'm going to get into that. But what bothered me most about this snippet is that it treats every individual signal source with the same priority that they all are dealt with. And when that's simply not the case, it doesn't take into consideration, you might not need to perform later checks if you've got some fail early behaviors, or just things, you have different behaviors or side effects, or different things. So you have to throw everything into this big combine to actually get any sort of output. And that's not what you want to have an ideal reactive data structure. So I'd like to take this opportunity to both introduce you to the concept that compose does not equal composed UI, and also introduce you to my furry feline friend, Cotty, named after Kotlin, who, after his namesake, has grown much fatter in recent times. Hello. So this is a really important thing to remember. Compose is not compose UI. Compose does indeed provide a wide range of Compose UI tools and UI tooling, but Compose exists as a concept, and it exists as a multi-platform concept with the JetBrains Compose plugin as well. So if we're only concerned with our business logic and our domain behavior, can we just kind of use these wonderful tools that we have in Compose already and just kind of throw away the UI stuff? Well, yeah, wonderfully we can. We can consume flows. We can consume flows with Compose loads that loads from the clouds. There you go, Alan. Feeding flows, and you can feed flows one by one. So you can sort of build a compositional state using property delegates to actually compose these together. I'm getting tired of saying compose. To compose these together, where you can actually give them the structural hierarchical element and importance they actually deserve. And you can use this magical recomposition of state most intelligently, because if you're only concerned with the parts that are actually changing, rather than throwing everything inside this massive combine function, you can only recompose the parts that you need. And finally, you've got this declarative job management, which you can decide on what you want to manage and which jobs to actually manage with the launched effect. And this all runs with the compositional coroutine state as well. So let's take that presenter and kind of feed it into our concept of a very naive compose-based presenter. So there's no omission of UI here. It's only preparation of a UI model. And there's plenty of compose talks that have been today that have been recorded that can explain how compose works under the hood, how compose works over the hood, how compose works from the side or from any sort of angle that suits you best. But I won't go into that because there's plenty of documentation already available. So let's just take this as a presenter. So how would we test this? We were talking about testability and how we can use UI models to build this test and build these things in a way that can be easily structured, where you can replay events, where you can have a predictive system under test. But how would we go ahead doing that? So generally fitting in with architecture, how are we going to test with presenters? And how are we going to sort of build these seams into our code? If you're familiar with the book on testing legacy code from Michael Feathers, he discussed about building seams into code where you can then kind of inject things and sort of behave and modify the system under state. So this is something we want to try and fit into our architecture, and unit testing is something very near and dear to me. I think it's my favorite kind of testing. Of course, it's only one element in the big testing pyramid, but you see so many projects that just don't take unit testing seriously, and it's an absolute crime. But if you've got compose code in your domain logic, then how would you go about testing that or unit testing that? Since there is already the expectation that compose is running in the UI. So the only tooling that is currently available for that is actually with Espresso. And I don't want to use a UI test framework to test my business logic. That's just ludicrous. So enter the concept of turning compositions into flows. So flows are very easily testable. We can test them with a kind of predictable behavior. So think about how we might write a sequence of flows. Something very simple here. We're just emitting a sequence of numbers with an artificial delay. And if you squint really hard, it might actually look very similar to what you'd implement in Compose. You're just producing the state here, and you're actually writing this to the thing. But you've actually got the same simple method signature, where you're actually just returning the actual value, and you can then recompose any number of times. So let's jump into the meat of Molecule and introduce sort of how this is actually working as a library, how it's recomposed as part of Jetpack Compose, and how it's running on this. So start off with a recomposer. Part of Jetpack Compose, and it sort of runs the composition. It's responsible for running the execution behavior, and it kind of requires a event loop, of course. We take this composition. This is where our kind of meat is actually going to be in there, and it's going to be handling the complicated slot allocation. But for the context of the composition, we only need to provide the recomposer. So this is handling all the kind of execution logic and when to execute it on the coroutine context. Well, it's really nice, actually, that it's using coroutines under the hood, because coroutines being a first-class citizen for Kotlin, it's very nicely integrated with Kotlin as a whole. The applier is the next step thing here, but it's not actually so important for us because, as we've mentioned, we're not actually working with UI, and the applier is the node management structure responsible for handling this UI slot table. And this might be appropriate for Compose UI on Android for using the composed web where it handles the DOM elements. But for us, we can just simply replace it with a non-operational applier because we're not really interested in what's going on there. Next, you want to launch a coroutine to actually start running the composer and start running what's going on here. That's just the kind of simple kind of structuring there. And we want to register the global write observer. So this is when something inside your compositional, your compose structure is actually changed. So I mentioned earlier about how compose is clever enough to detect recompositions. And if something in your composition has changed or has become dirty, then that's going to trigger a global write to actually then update with the global state. But this can happen pretty frequently, so this is actually quite a naive way of doing so. So you might actually end up in a situation where you've got five invocations straight away, and that's just going to cause unnecessary work, especially when we're not working with the UI. So we're going to sort of conflate that with a channel so that we're actually not receiving these all the time so quickly, and if we say get 5 in one go, it's just going to conflate that and make sure we only have to do it once. Rate limiting. Next, we'll actually send the apply notification. As mentioned, this is going to be rate limited now. And finally, we're actually kind of setting up the content. So this is from the block that you'll actually set the content in. You'll recognize this set content from compose view or activity where you set the content as an extension method under the hood. It's just creating compose view anyway. So yeah, this is all this is doing here. And for Molecule, it's creating a callback. So this is just to handle some top-level application stuff, so behaviors and supports. Nothing really important, but it's just a callback. And finally, because we are good citizens, we're going to handle our cleanup operations. So we dispose of the composition and the snapshot handle. And this is handled on the invocation of closure on the context. And that's it. And that's what I found really quite interesting about Molecule when I started getting to know it a little bit, because something so advanced or something seemingly revolutionary is composed in our environment. It's like, wow, this must have like some black magic underneath, some voodoo stuff going on. And it's like, then you actually dive into it and you find out it's actually not all that complex. It's quite straightforward. And then when you realize that it's not so straightforward, the idea of using it in environments where maybe it wasn't meant for UI, it's actually not so concerning. So yeah, it's surprisingly simple. There are some things to take into consideration. As I mentioned, you are going to need your state to be, dirtied so that it knows to actually kind of recompose. So for this, two things are going to happen. For the recomposition, you're going to need to have the content must be dirty. This is going to happen when something in your composition has been marked as out of date. This could be, a flow that re-emitted another item. It could be just a value state that changed some input. It could be anything. But the point is that your current composition is dirty. And then you're going to have to get another frame clock that's going to have to tick. Now, in most environments, this is going to be the scheduler from Android, but it can be, any sort of coroutine context that you're going to feed into it. And the interesting thing as well is that this dirty state is persistent. There's lots of wordplay there, which I'm just going to skip. The dirty state is persistent, so it's going to stay dirty until recomposition, but you're going to have to wait until the clock ticks to actually then trigger that composition. This is why you need both the fact that it's dirty and that you get a frame tick. If you get a frame tick without the dirty flag, then it's just going to do nothing because it sees the state as equal. So Molecule exposes two APIs for usage, one with the current Steam scope and one without. The only difference between these is that one is producing a flow and one is producing a state flow. Flow is probably going to be important for if you're working with tests, where you want a cold flow or sequence of operations that you can replay, that you can test which have been emitted. And state flow is probably more pertinent for working in production environments where you're really only concerned with the current state that you can then observe and start to check. And it's going to be conflating the result as well. So, you don't really care about the sequence of operations or replaying that. Then when you combine that with Turbine under tests, Turbine is a great great library from the Cache App team, where you can test flows. It has no affiliation with Compose. It's just simply for testing flows. And it provides a really nice, simple framework and simple API for working with flows. The implementation is also remarkably simple if you want to dive into that, but you don't need to. And if you remember the early days of flow testing, when flow was still experimental, the test approach to this was actually really messy. You'd end up setting up an asynchronous channel and then observing these set results and then launching your execution assertions, and you can never really be certain if you are handling it in the right way. So obviously there are pros and cons to this. So composables are sort of state flows, essentially. They'll always be able to kind of query the current state. So you'll just be able to ask the composition what the current state is. And this is actually really important if you're working in a production environment, because you might have business logic and you might have a UI that can't wait for the business logic to execute. It needs to know the immediate value of what are you now. You can't really do this with a flow, so the meaning is not really contextual in the same way, and the number of items emitted by this is dependent on how many times the recomposition has triggered, which is not always predictable, and it can be a bit kind of unclear. So an example about how to run a test for this, and this is a bit messy code here. It was written pretty quickly, so please don't judge. But we're just sort of calling the presenter here, asking it to provide us with a list of elements that's happening there. So we're calling molecule flow, which produces a flow, includes in the name. And we're using the context clock. So molecule requires you to provide a clock of some kind. You can specify that you're using context clock, which will infer the clock from the coroutine context that you've got there. So in Android environment, in production environment, this is going to be your native choreographer. And this is okay in some circumstances, but it's a bit difficult to work with under test. So if you wanted to write a unit test with the choreographer, you'd have to then yield before each execution to then make an assertion. You have to kind of drive this choreographer forward. And it's requiring the frame clock to be dirty as well, find the state to be dirty as well. So take an alternative to that, and you've got something that's using the immediate clock. Now this is comparable to the unconfined dispatcher in coroutines, although dispatchers.main.immediate. And it's kind of similar to this, or using run blocking, for example. And what it's going to do is just provide you with the next frame available. So it's going to make sure that your recomposer is never waiting, and if it's asking for a next frame, it's going to get it straight away. And this is really useful for writing unit tests, because then you can make your assertions straight away. But you can also use it in the same way that we'd use run blocking with some compatibility frameworks working with maybe synchronous APIs or RxJava. There is a bit of a downside, which I haven't found a solution to yet, but that's been using, you have to use the yield to actually trigger the first launch effects or initial launched effects, if you have those. And the rest of the events can be treated with a normal sequence of flows, normal sequence of iterations in a flow. So using the turbine assertion logic here, you can see it's much simpler to test your domain behavior. And remember, this is all coming from a compose block. So you've got this presentation logic triggering this compose stream of UI states and UI models, UI states, and it's all kind of given to yourself as a flow, which is really cool. So nitty-gritty bits to the side now, and this kind of got me thinking about what is the role of architecture in this sort of setup. So if we're moving more towards having more of our code in Compose, then where do elements such as the architecture components from Jetpack come into play? Like, is it possible to create an entire application in Compose? Could I just stick to Compose only? You can. It's not so easy, but also not so justified. So, most specifically, I was thinking to myself, well, let's look at the Jetpack view model. Now, this is a great solution to a very difficult problem that we've all been faced since the dawn of time, apparently, that we have configuration change in Android. Our entire world will be destroyed, and we'll have to recreate it from scratch every time something changes. Now, view models handle this in a quite nice way. There's lots of kind of complex behavior under the hood with headless fragments. But it was a way of handling your state. You can have a state inside of a view model. You could have some complex, maybe some expensive object creation inside there, and it would be persisted through configuration change. But I was thinking, well, if we're moving to a compose environment, is a view model still necessary? Can I drop this and not have to worry about this anymore? And it really comes down to your host environment and thinking about what's going on. I mean, whilst we are in a composed world now, we're still running on consumer hardware. We're still running in an Android activity. So we are still subject to this view lifecycle of the activity that is going on. So my initial thought was that, no, we can't really escape this, even though the lifecycle of composition is much simpler. Just recompose 0 or more times. It'd be so much life would be so much simpler if it was just this and not this complicated life cycle. But then I was talking with Bill and sort of had the idea that, well, actually, what if we treated the view model as a first-class citizen, and instead of having everything from our activity, we just had like, okay, we'll just keep our compositional state in a view model, and then the view model is persisted, and if we treat that as the root, then it kind of works, right? So the recommendation for using Compose in a view model is quite simple, and using coroutines here as well. So we're using immutable state here. It's just a traditional Android X view model whose responsibility it is to store the state. It's also extending from the view model class, which is an abstract class, which is what's handling the complex state persistence in the background, and then the state is consumed in the rendered representation in that state of form. So then you might have something like a molecule view model that is, using molecule to launch this with a context clock, and then using UI models. So the view model's responsibility here is purely a scaffolding. And then you've got the login screen, which is then actually calling that and using this to persist it. So it's quite a nice way of using your view model as sort of a root container for your sort of compose behavior. So then you're still moving all of your compose stuff into a presenter, which is creating all your UI model stuff. And then it's just being persisted through a view model. Then I got to listening to a few podcasts and some discussions from the ADB team, and then there was the thought proposed that, well, actually, what if we just disabled the system handling of config changes, and then we have our activity handle config changes, and we have this wonderful little tag in the Android manifest that says, you know what, I've got it, I can do it. So then you're observing the configuration change in your activity, and then your activity doesn't actually get destroyed. Ergo, if you're using remember savable to persist anything in your composition that is necessary for persistence through application restart, you can actually forget about using view models altogether and forget about the whole configuration change, because your resources that will actually be following from local configuration will be changed as and when the configuration is changed. So theoretically, we don't actually need this anymore. Of course, you're still subject to transaction too large exceptions, so don't go over 1 megabyte. But it actually can be better to use remember savable, because this is actually going to be restored through the saved instance state, the saved state after application restart. Whereas view models are only able to survive the activity death. There's also a lot of other architectural elements that sort of popped up over time as well with Compose. So there's a great library that's being maintained by Zach and the folks at Slack. And it's sort of handling navigation in a Compose environment. You might be familiar with using the navigation libraries with Compose from Jetpack. But there are lots of other options that have multi-platform support. I'm a big fan of multi-platform, so I'm going to go with that. Here you've got just a parcelized object that's representational of the screen, and you've got a simple backstack and the navigation paradigm going on there with on backpress and backstack. Another element that's really cool, another library, sorry, is one from Arkady. He gave a talk on it yesterday, I think, on Decompose. It's kind of similar to Circuit, and it's got a lot more kind of behavior with it, and it's been developed for a little bit longer. But it's handling this navigation stack behavior in a Kotlin Compose multi-platform environment. Obviously, it doesn't have to be Compose, but it works really well for that and provides abstraction of the platform lifecycle configurations and navigations. Perhaps a bit hard to read, but yeah, you're creating a root component that is a representation of an element. So it could be representation of an activity or of a fragment or anything you like, but it's importantly not tied down to the platform types. So closing up, the resources for this are available online on GitHub. This is all the kind of code samples, and this is my second cat, named after Python. He has a habit of lying in uncomfortable positions, which apparently are very comfortable. The slides will be available online. And that's everything. Thanks.